Okay, cool. Yeah, so back into the presentation. So just to get you guys, just to get you a little bit excited about using tensor networks in like real world applications, we had a resident last year develop this demo for us. So you can't really read the text because it's kind of small, but on the left here, what we have is we have a transformer model that's just doing like sentence generation. So this model was trained on the billion-word data set, which is mostly just like New York Times articles, Wikipedia articles, etc. And all it is doing is it's just generating a sentence word by word by giving a probability distribution of what the next word is, sampling out of that, and generating the sentence that way. On the right, what we have is we have the exact same transformer model, but what we did is we took the dense, fully connected layers of the transformer model, and we replaced them with these tensor networks. Specifically, the type of tensor network that we use to replace it is something called a matrix product operator, or an MPO. And as you can see, the inference time on the tensorized or the tensor network version of the transformer is about twice as fast as the original version. Which, if you're doing, machine learning programs that are supposed to run in production, so things like sentiment analysis for YouTube, things like the BERT model for Google search, those are the types of things to where like the latency really matters. So being able to have these big speed ups for your production models actually is incredibly useful. Great. So with that little taste of a demo of like things to get excited about, this is basically what the presentation is going to be. So the first thing I'm going to do is I'm going to just talk about, what the heck are tensor networks? What do they actually represent? Then I'm going to be going into a little bit of the tensor network library, the API, and how to use that to build your own tensor networks that you can run for your own machine learning models. And then I'll go into some, past research experience using tensor networks using just tensor networks for machine learning, as well as using tensor networks to simulate a quantum computer. And then finally, I'll be going into details on how the demo I just showed works in practice and like all the details of that. So great. With all of that said, I'm sure this is a question that everybody is still asking, is like, what is a tensor network? Well, a tensor network is just simply a network of tensors. Pretty self-explanatory. So if you guys ever use TensorFlow, I'm sure you already know what the definition of a tensor is. But if you don't, I'll just be explaining that here again. So tensors are basically just fancy / generalized matrices. And by generalized, what I mean is, so a matrix, you can store a matrix in like a 2D grid of numbers. With the tensors, instead of being a 2D grid of numbers, it can be an arbitrary D order set of numbers. So for example, things like scalars are tensors that are order 0, which means they just have a single number and there's no like dimension to it. Vectors are tensors that have order 1. It's basically just like a 1D list of numbers. Matrices have order 2, which basically means it's like a 2D grid of numbers. Order 3 tensors, can be like a cube of numbers. You can have order 4 tensors, which would be like a hypercube of numbers, etc. So this goes up to an arbitrary number of dimensions. But really, all a tensor is it's just some like block of numbers, and these numbers can be real or complex numbers. And so how we actually represent tensor networks, or actually how we actually represent these tensors within the tensor networks, goes by their nodes and edges. So a node in a tensor network is the actual concrete tensor. So that node represents like your actual tensor that you would have. And then the number of edges coming out of that node actually represents the order of the tensor. So usually what I have is I'll have like a crowd of people and I'll have them shout out what kind of tensor this is. But since we're all on Zoom, I'll skip that step and I'll just shout it out loud on my own. So in this case, what I have is let me get a pointer open. What I have is I have a tensor with a single leg coming out of it. And so this type of node with just one edge would represent what you would normally call a vector. So a matrix is going to be a node with 2 legs coming out of it. A scalar is just a node with no legs coming out of it. And then finally, an order 3 tensor is going to be a single node with 3 legs coming out of it. And so that's basically all like a tensor network is. It's just a big connection of all of these tensors like connected together via their edges. So another important thing to note is, so what happens if I have two nodes and they're connected via an edge? Well, what that represents is this edge represents a dot operation that you can apply on these two tensors on this axis. So in this case, what I have is I have a vector here. It's connected to another vector here. When I contract this leg, or when I contract this edge, which basically means I remove the edge and I merge these two nodes together, that's called an edge contraction. And what happens is, mathematically, when you do that contraction, that's actually doing a dot operation, or like a you can effectively think of it as like a map mall. So in this case, what I have is I have a vector dotted with another vector that's going to give me a scalar output. So this type of operation is what you would normally consider like a vector inner product or like a vector dot product. You can also represent slightly more complicated operations. So in this case, what I have is I have a matrix. It's connected to another matrix via one leg. When I contract this leg, these two legs stay the same. You know, these are just dangling legs, which I'll describe in a bit. So after I contract these two things, I'm left with another matrix. And so this type of operation is when I dot these two matrices together. This is going to give us another matrix. So this type of operation, or like this type of tensor network, would represent what you would normally consider a matrix multiplication. Cool. And then finally, these things can get super crazy. So in this case, you know, I have some crazy amount of, so I have 4 of these order 3 tensors, each of which are connected to each other in like this crazy way. But what I can do is I can fully contract this tensor network, and I know that my result that's going to be left over is going to be a scalar. And so there's no special name for this type of network contraction. This is just a normal tensor network contraction. Cool. Beautiful. So yes, so let me give a really short overview on how to do these types of things within the tensor network library. So the tensor network library is mostly just about nodes and edges. And so how to actually build these nodes and edges looks something like this. So I don't have it at the top here, but basically what you would do is you would just have import tensor network as tn and import numpy as np. So here what I have is I have 2 nodes that are just filled with ones. You know, it doesn't, for this example, the data doesn't matter. It's just a very simple example. And so after I run these 2 lines of code, what's going to happen is A and B are going to represent nodes. And they're going to automatically, so these node objects are going to automatically generate these dangling legs as such. Excuse me. Next thing what you can do is you can connect 2 dangling legs together. So in this case, I have A with its second axis, and these have 0 index, so really it's like its third axis, but yeah. The second, so A's second axis being connected with B's first axis. So there's 2 ways of doing this. You can either use tn.connect if you want to make it more readable, or if you're connecting a lot of things and you don't like typing that much. We've aliased the XOR operation to do the exact same thing as tn.connect. And the reason why we picked the XOR operation is because it kind of looks like 2 legs or like 2 lines connecting against each other. And so that's why we picked that. So after you run this line of code, what your tensor network is going to look like is something like this. So after I run this line of code, the A and B edges are going to get connected together, and they're going to generate this new object that's just going to represent the edge. So this edge object is literally representing like this connection between A and B. Finally, what you can do is you can contract these 2 nodes together. So when you contract them, the best way of doing it for the most part is to use either this @ operation or this tn.contract between. These 2 operations are going to do the exact same thing. And so what this is going to do is this is going to find all of the legs between A and B and contract them together at the same time. And I'll be going over later in the presentation as to why that type of contraction is much more optimal than doing it 1 leg at a time. But yeah, so after you type up this 1 line of code and you run it, your tensor network is going to look like this. So you guys can't see my face right now, but basically what happens is these 2 legs and then these 2 legs of B actually get moved down And so these two legs are actually the same edge objects that were on A before, and these two legs on C are the same edge objects that were on B before. And so after you run this contraction, what happens is the edges of A and B get reset, and they're given what's quote unquote called fresh edges. Alrighty. And so this is a shorter way of writing it up if you don't want to type out a bunch of these like tn.connect calls, but I won't be going over that too much. Great. So before we go on, let me finish up some really basic terminology just so everybody is aware of the vocabulary that I'm saying. So when I mean a dangling edge is a edge to where only one side of the edge is connected to a node, and the other side is just left free or is left dangling. These type of edges don't represent any type of computation that you would run. And basically what it is if I set up a tensor network and it has 3 dangling legs, after I contract all of the nodes together, my final result is still going to be a single node with 3 dangling legs. So basically the number of dangling legs in your tensor network is going to represent like the order of your output. The second type of leg is these legs called standard legs. We've already gone over this. These types of legs are just legs that represent doing a dot operation between these 2 axes of this tensor network. And then finally, the type of leg that we haven't talked about yet are these things called trace edges. Now, trace edges are edges that connect a node back to itself. So you might be asking, well, why does this one have like a special name? Why is this called a trace edge? Well, the reason why this is called a trace edge is because this operation, if I was to contract this leg, I would be going from a matrix to a scalar. And the actual operation we run when we contract this leg is taking the trace of A. So basically like just summing down the diagonals. So that's why we call it a trace edge. Woohoo, demo time. Okay, so if you guys want to follow along on your computers, go ahead and go to github.com/Google/Tensor Network. I'll give you guys a little bit of time to copy this link if you want to follow along. If you don't wish to follow along, that's totally fine as well. And I think that's enough time for people to type out the URL. So I'm going to go ahead and click on this.
Chase, actually, I guess whilst people are doing that, we have a question.
Yes. What's the question?
Yeah. So someone asked, are edges directed? If not, why?
No. So the edges aren't directed. And that's actually a really good question. So why aren't edges directed? Well, the reason why is let's say if I go back to this vector product, the dot between A and B is actually going to be equal to the same dot between B and A. And so because dot operations are, I think commutative is the right word to use, it doesn't matter what order you contract these things in, and it doesn't really matter what order these things get connected to. So with just a vanilla tensor network, these edges are not directed, so they're undirected edges. There are certain types of tensor networks that do have directed edges, and these type of edges are things that they're generally called like symmetries, and so these have some type of structure that we can exploit to get faster inference time, and most of the time they relate to like charges of electrons or like charge flows of electrons, but that's very much out of scope of this conversation. So for all of the tensor networks that we'll be seeing in this presentation, all of the edges are going to be undirected. Yep, good question. Thank you. Are there any more questions?
Yeah, we have another question. How is tensor network faster than dotting tensors in NumPy?
Good question. So it's not. And in fact, if you actually look in the tensor network code just inside of NumPy, that's basically what we're calling is just numpy.tensor.operations. So it's not really that the dot operation is going to be faster with tensor networks. It's that tensor networks are used to approximate what a much larger dot operation would actually be doing. It's just using substantially fewer floating point operations. And I'll be getting much more into that later down the line as to how do we do that type of thing and how do we get these speedups. Is there another question? Is there another question?
Yes. Actually, I think we'll just hold off on these questions until the demo.
Okay. Cool. Yeah. So let me go ahead and share a different screen. So I apologize for the I'm just going to share a different Chrome tab. Can everybody see this GitHub page?
Yeah, I can see it at least.
Outstanding. Great. So yeah, so if you want to follow me along on this demo, go ahead and go to the github.com/Google/Tensor Network. If you just Google Tensor Network, it'll probably be like the first link that pops up. And then if you scroll down to tutorials, so for today, the one I'm going to be going over is just the basic API tutorial. So if you wish to follow me along, just go ahead and click on this link. I'll give people a little bit of time to find this link and follow along if they so choose. We'll give like another 10, 15 seconds for people to be able to get this collab open and follow along. And I think that was enough time to wait. So I'll just go ahead and click on this myself. Great. So yeah, so this is just going to be going over the basics of how to use the Tensor Network library and how to get and how to build and contract these different tensor networks. Cool. So to get this started, just go ahead and click Open in Playground. And then you're going to want to Shift Enter. So all this is going to do is this is just going to install Tensor Network along with installing JAX. And so JAX is how we run things is like the preferred way for us to run things on GPUs. But I won't get to that until the very end of the presentation. So yeah, so you'll click Shift Enter. You'll get this little warning that said this was not generated by Google. This is my personal email. There was some hiccups getting my Google email attached to this. So just click Run anyway. Cool. So this is just going to install Tensor Network along with JAX. And great. So let me go ahead and just zoom in a little bit so that the code's a little bit easier to read for people who are just looking on the Zoom. Awesome. So yeah, so this is basically just going to be running very similar code that we had before. So basically all we have is we just have two vectors, A and B. They're both going to be represented by nodes in the tensor network. Then all we do is we just connect the 0th leg with A with the 0th leg of B. We contract this leg, and then we get our final scalar output. So if I click Shift Enter on this, we see that the inner product of np.1s with np.1s is 10.0. Woohoo, great. Some more details about how Tensor Network actually works. So when I do this A index with an integer, if A is a node, then this index of this integer is going to give you the edge that represents that axis of that tensor. So in this case, I have a 2x2. I have a 2x2 identity matrix, and all I'm going to do is I'm just looking at what is the type of the first leg of A. We can see that it is an edge type, and then what we can do is we can ask is A0 dangling. Since I haven't connected A0 to anything, we'll see that that answer is in fact true. We can build trace edges with this same node. So if I do trace, I can build a trace edge by connecting a node to itself. So here I'm connecting the 0th leg of A with the first leg of A. So that's going to create a trace edge. When we create a trace edge, what happens is the original two objects that represented the edges originally effectively get deleted. And then A0 and A1 get updated to actually hold the same edge object. And that edge is going to represent that trace between A0 and A1. So if I actually look at are A0 and A1 the same edge, so basically I'm asking is A1 or is A0 A1, we see that that returns true. And then we see that A is no longer dangling as it's just a trace edge. Awesome.
Actually, we have a question.
Yeah, so, I can't see to get this set up, I can't really see the question. So if you see a question on the Q&A, please just the Stanford people just shout it out.
Yes.
Really would appreciate that.
Yeah, so awesome. One of the questions is the idea of tensor networks similar to a generalization of low rank approximation?
Yes, exactly. And I'll be getting into that later down the line. I'm just giving like really basics right now.
Perfect, thank you.
Is there another question?
Another question is if contract is dot operation, to clarify that.
Yeah, so tn.contract is the dot operation. This one, so tn.contract will contract an edge versus tn dot, let's say, actually it'll be easier if I just use the above example. So yeah, so here I had tn.contract. So this is still just a dot operation, and it's going to dot like the two axes that's defined by this edge. I can also just, and actually this is the preferred way of doing it. I can also do contract between A and B. And so this is going to contract all of the edges between A and B. And we'll see we get the exact same result. So contract and contract between basically do the same thing, but a little bit different. And I'll be going over the difference later in the presentation. Is there another question?
Yeah, there was actually a question about whether like when this notation would be more useful than Einstein's notation.
Yeah, that's a great question. So when would this notation be more useful than Einstein notation? And the answer is if you have like dynamic graphs. So for example, I'll be giving an example to where we want to do a sweep of an MPS. And those types of things aren't really possible with just a simple einsum. Also, if you have a tensor network with more than like, 5 or 6 nodes, that einsum expression is going to become very quickly unmanageable. Versus this more object-oriented notation of tensor networks makes building and debugging these things a lot simpler. So yeah, you can always write a tensor network as an einsum, but there are lots of situations to where actually using the TN library is going to be better than using einsum, just because it gives you a lot more flexibility. I hope that answered the question. Is there another one? Hearing nothing, I'll assume the answer is no. Great. Yeah, okay, so here's the question. So here is one of the things I promised to bring up earlier is, okay, so we had these tn.contract and we had the method tn.contract between. Why would I want to use one versus the other one? And so the answer is, unless you know what you're doing and like you specifically want to like only contract an edge for whatever reason, you're pretty much always going to want to use either the @ symbol or the tn.contract between. And here's an example of that. So here what I have is I have 2 matrices, each of which are going to be sized 1000 by 1000. And basically all this tensor network does is it just takes the trace of A times B. So yeah, nothing too fancy about that. But these 2 methods calculate the trace of A and B in 2 different ways. The first one just contracts each edge individually, versus the second one actually uses contract between. And what we'll see is the contract between is actually going to be a lot faster than using one edge at a time. And I'll explain why that is in a little bit. So yeah, we'll see that using one edge at a time takes 66 milliseconds versus using contract versus using contract between takes like less than 5 milliseconds. So we get like over a 10x speed up just by using contract between versus contracting one edge at a time. And so I'm going to stop this and I'm going to switch over back to my slides. Beautiful. And then I'll skip the GUI. Let me just skip ahead so I can explain the contract. So here's a question. Why did using contract between, why was that more optimal than contracting one edge at a time? Well, let's actually go through why that happened. So what happens is when I contract just one edge at a time, that looks like basically doing this. And so after I contract this one edge, I'm going to be left with this trace edge here. And remember, trace edges only sum up the diagonal of this matrix. So all of the memory and all of the compute I use to calculate all of the off-diagonal entries, which if your tensor is large is going to be a vast majority of those elements, all of that time and all of that memory gets totally wasted because you don't use it for anything. You're only summing the diagonals in this next step, and the rest of the The rest of the numbers that you calculated get totally wasted. And so what you prefer to do is you prefer to contract both of those legs together at the same time. And you can do that very easily with just tn dot contract between. Yeah, so I hope that answered that question. And I got a little bit ahead of myself, so let me go back to this question. So yeah, so let's do a slide aside and let's talk about one of the really beautiful things about tensor networks. So here's a question. If I have these three arbitrary matrices, such that, you know, each of these like three multiplications are consistent. So maybe A is size 1000 by 10, maybe B is size 10 by 5, and maybe C is 5 by 1000. So each of these three multiplications line up. But these multiplications are going to produce, you know, wildly different matrices. They're different shapes, so they're certainly not equal. So the question is, are the trace of these three operations the same? Now, if you've taken linear algebra, you know the answer is yes. But also, if you've taken linear algebra, I challenge you to actually prove that this is true. And you'll find that actually doing that proof is somewhat involved and is actually kind of complicated. However, I'm going to prove it very easily with a tensor network. So let's do that. So first, let's just build the tensor network that represents the trace of ABC. So to build the trace of ABC, all I have is I just have my A matrix here. I connect up A to B right here. And then to do the dot operation between B and C, I connect this leg right here. And then finally, to be able to take the trace of this final element, all I do is I just connect what was originally the dangling leg of A and the dangling leg of C. I just connect them together. So then I'm left with this triangle-looking tensor network. You'll also notice that the trace of BCA can be built pretty much the exact same way, to where I just connect B to C, C to A, and then I connect the two remaining dangling legs together. I've given this triangle. Finally, that's also true for the traces CAB. But what you'll notice is that these three graphs are isomorphic to each other, or, you know, they're basically equal. And the only difference between these graphs is they're just like a rotation of each other, which in tensor network language means absolutely nothing. So it must be the case that these three calculations are exactly the same. Boom, there's your proof. This is one of the things that I really love about tensor networks. And what's also really cool is tensor network notation. So actually like drawing these graphs is just as rigorous mathematically as doing like Einstein notation that you would do in maybe like a physics proof. And so this is one of the really cool things that I love about tensor networks. And in fact, at our job, a lot of the times when we're like drawing calculations or like doing mathematics for whatever problem we're trying to solve, you'll see we'll have like, you know, the sigma for the sum, and then we'll draw a tensor network. And then maybe on the side, we'll have a tensor network wrapped inside of maybe like a log. And so using these tensor networks as mathematics does actually work. And we do it all the time at my job. And it's super, super cool. It's one of my favorite things about tensor networks. Cool. We already went over this. Awesome. Part 2. So I remember there was a question earlier in the presentation about, do tensor networks represent a low rank like approximation of matrices? And the answer to that question is yes. And so in this part, I'm going to be going over how do we actually do these low rank representation of these like much larger matrices. Cool. So the main operation we use to what we, you know, quote unquote, decompose a larger tensor into a tensor network is through this operation called splitting a node. So I've gone over merging nodes, or like contracting edges to merge nodes together. That's pretty straightforward. That's just a dot operation. But going in reverse can be a lot harder. And so to actually split a node to go in reverse, to do that, what we do is we actually take the singular value decomposition of this node. And so you might be asking, like, Chase, SVD takes one matrix and turns it into 3. How do you go from one matrix to 2? Well, let me explain that. So the technique that we use inside of tensor network looks something like this. So basically what we have is we have M, which is going to be our original tensor. We decompose this M into our U, S, and V components. We take the square root of S and we split that into 2 nodes. So if I was to merge these 2 nodes together, that would just give me back my original S, or my original diagonal S value. And then finally, we merge this S into this U, and then this S into this V, giving us U prime and V prime. So these are no longer unitaries. but they're still like, very useful tensors. And one of the things that we actually do, and is a thing I'll be describing, like that a real use case of doing this later down the line, is when we actually take this step where we take this square root of this S and split it into 2 nodes. At the same time we're doing this, we drop the lowest singular values. And so what that does is that allows us to effectively compress our matrix into a low rank representation of what it was before. So let's say M was, a somewhat large matrix. Let's say it was maybe like 1,000 by 1,000. But let's say we only keep the top 10 singular values when we do this low rank approximation. So after we do that, the total number of parameters in our original M is going to be 1,000 by 1,000, which is 1,000,000 parameters. However, if we only keep the top 10 singular values on this dimension, this is going to be 1,000 times 10, which is 10,000, plus 1,000 times 10, which is 10,000. So then this would only be 20,000 parameters. So that would be like a 50x reduction in the number of parameters of our original like operator, just by having it be a low rank representation. And so another question might be, so how do I do that with an order 3 tensor? Well, it's pretty straightforward. Basically what you do is you take these 2 edges and you just flatten them together. So it's basically like if you've ever done like np.reshape, if this was size 10 and this was size 10, we would merge these together into a single axis of size 100 and then just split it as if it was a normal matrix. And it's nothing more complicated than that. Cool. So with that in mind, I'm now going to be jumping into the more interesting things. So the first thing I'll be talking about is doing tensor networks for quantum computing simulations. If you don't know what a quantum computer is or how they work, don't worry about this section. It won't be very long. It'll be maybe like 5 or 10 minutes. If you do understand how these works, then you can actually utilize the tensor network library to build these circuit simulations. And in fact, we do that at Google all the time. Yes, question.
Maybe we should go over a few questions before we go into a different topic. So yeah, one is there a difference between an edge and an axis?
Is there a difference between an edge and an axis? Yes and no. So an edge represents an axis on a node, or on the tensor that's represented by this node. So yeah, you can basically think about them as being equivalent. So an axis is, an axis on a tensor, and an edge just keeps track of that axis, if that makes sense. Any other question?
Yeah, we have another one. How can you visualize the network graph?
Great question. And I will show you how. So let me switch back over to my Colab. Cool. Let's actually do that right here. So what you can do is you can just do, actually I didn't want to do quite there. You can do tn.toGraphViz, and then you just pass in your list of nodes, and it'll give you a visualization of the graph. You can also name them to help keep track of stuff. Yeah. So yeah, toGraphViz. That's generally how we visualize our graphs.
Great. And we have one more question. Yeah. Is SVD, it's a question talking about SVD and TensorFlow versus SVD and tensor network. What are the differences, like a speed comparison? Is one better for larger data sets?
No, SVD. So so here's the thing. Tensor network is just a wrapper on top of all of these different libraries. So tensor network is basically just like a higher level library on top of these other backends like TensorFlow, NumPy, JAX. So when we do SVD of a tensor with like the TensorFlow backend, all we're doing is we're just calling TensorFlow.svd. It's just that the tensor network library helps you do a lot of this axis bookkeeping. Because if you try to like do this SVD and like do the reshaping and transposing by hand, you very quickly are going to run into bugs that are very difficult to find and fix. Versus the tensor network library helps you do all of this bookkeeping and keep track of things much more easily and helps you accelerate your research. Does that make sense? Is there another question? Hearing no response, yeah, I'll take that as a no.
Thank you.
Awesome, thanks. Yeah, and again, I have these things in like 2 different windows on my screen, so I can't see the Q&A. So if you do have a question, just like, well, I mean, fill it out in the Q&A, and then I'll have like Jessica and Peeps just shout it out at me. Great. So going back to my slides.
Actually, Chase, sorry, we have one more question before I move on. And is using NKhan faster in any way, or is this purely for convenience?
Purely for convenience. So yeah, NKhan, if you read the code, all NKhan does is it just takes your like dense code and just builds it as a tensor network and contracts it. So it's running this, it's using the same code path. It's just like a different API that's a lot more condensed. And there's some use cases for it. I don't know. Some people use it, some people don't. It's just another API.
Great, thank you.
Awesome. All right, cool. So next thing I'll be going over is tensor networks for quantum computing simulations. So if you've ever seen a quantum circuit diagram before, what's awesome about quantum circuit diagrams is the circuit diagrams 100% map to tensor networks. So if you give me a quantum circuit, I can give you a tensor network that represents that quantum circuit 100% of the time. Cool. So with that in mind, there are some things to be aware of when you do these circuit simulations using tensor networks. So what's actually interesting is a qubit on a tensor network, or a qubit that's represented on a tensor network, is not actually a node. Qubits are actually represented by the edges of a tensor network. So a qubit is actually an axis of your wave function, which is super cool. And so the qubits are the dangling legs. So let's say I wanted to take an operation on the first qubit. Let's say I wanted to take like a Hadamard on this qubit, or like a Z or an X operation. To do that with a tensor network, basically what you do is you take your operation node that will have two legs, an input and an output leg. You connect your input leg to the qubit that you want to do the operation on, and then the output leg of your operation now becomes like your qubit post doing the operation. So if I was to contract this node into what is the wave function of my quantum computer, this leg now becomes my qubit that I can do other operations on. So if you know quantum computing, or if you know quantum physics, that might seem super cool. If you don't know these things, totally fine, because that is the end of talking about quantum computing. Awesome. So let's see, we have about an hour left, right? Yes. Okay, cool. So then I get to use all of my slides. So let's talk about using tensor networks for machine learning. So this is going to be broken up into two parts. The first part is going to be tensor networks, like just using tensor networks for machine learning. And then the second part is going to be showing off how to do hybrid tensor network, neural network machine learning applications, and how you can use tensor networks to speed up the inference on your machine learning models. Cool. So I'll be going over an example of how to use only a tensor network for machine learning. Just to keep everything basic and simple, since we only have about an hour, the only example I'm going to be going over is doing binary classification on a binary, on bit string inputs. Tensor networks can be used for like image classifications. They've been shown successful for like MNIST type things. But just for this presentation, I'll just be going over the most basics, just to give you for a feel of how these type of things work. So here's a question. Let's assume I have a perfect classifier. Is it possible to have a binary function with binary inputs be represented perfectly by a single tensor? So the answer to this question is yes. But the problem is that perfect classifier tensor becomes unusably huge. And so that type of tensor looks something like this. So it's a crazy, crazy high order tensor where every single one of the elements in this tensor are just ones or zeros. And so basically what this tensor represents is this is just a giant lookup table of your inputs. And so how we actually contract this tensor network to get like the final result of it looks something like this. So basically what I have is I have my binary input represented as just a bunch of vectors. So if I have a 0 bit, I can represent that just via this vector, just this 1 0. if you're into physics and you've seen bracket notation, that's the same as a 0 ket. As well as if I had a 1-bit, that can be represented by this vector, where instead of having the 0 being the second place, the 0 is in the first place, and that's represented by this 1 ket. And so if I had a bit string on my function that I wanted to like an answer for, what I would do is I would connect each of my bits via these vectors as such, and I would just contract this entire network. So I would just contract every single one of these edges, and this is going to give me a result. So in some situations, after I contract this thing, this might give me a 1, and in some other situations, this might give me a 0. And like I said before, this giant tensor basically just represents just a huge lookup table. And so this tensor right here is just a big pile of 1s and 0s. But the problem is when using this huge tensor for machine learning applications, it's pretty much like if I just had this one huge tensor, it's pretty much useless for ML. And the reason why is because, one, this thing is huge, and you're basically just like memorizing your inputs. So if you have more than maybe like 10 or 20 variables, this is going to become unusably large for any practical application, as well as how would you train this type of thing? Like, if I have a data point and I wanted to train this matrix to update that data point, well, pretty much all I could do is just go to that index of this tensor, switch a 0 to a 1 or a 1 to a 0, and that's basically it. There would be really no way to like generalize this tensor. However, if we were to decompose this tensor into a tensor network, then those type of problems go away. So this type of tensor network is significantly smaller than this tensor. So let's say each of these dimension of these legs were size 2. If I had 100 legs, this thing would be of size 2 to the 100, which is more than we have atoms in the universe. However, if I was to decompose this tensor into this much smaller, what's called a matrix product state, or an MPS, and let's say, maybe these bond dimensions was also size 2. So each of these tensors really only has 8 elements in it. So if I had 100 of these, then I would only have 800 parameters, plus or minus, these n guys. So I would have less than 800 parameters to approximate what this huge function would look like. And so instead of doing machine learning on this huge tensor, we're going to be doing machine learning on this tensor network. And again, this thing is called a matrix product state, or an MPS. So there's 2 ways to train an MPS. The first version I'm going to be going over is going to be really straightforward and simple. And then the second version is going to be using tricks out of quantum physics to be able to get a better classifier out of this. So the first thing we do is we treat this tensor network just as we did normally with our big tensor. So we contract this thing, we're given some results, and then to be able to train these blue nodes that are our model of the tensor network, basically what we do is we take the loss of whatever our model output from what we expect our model to do, just do normal gradient backpropagation against these nodes, and then take that gradient, slightly update each node, and then do that every single time for the different digits that we have, or for the different like samples that we have in our data set. So this is like, I'm sure if you've ever trained a neural network, this looks very similar. You have your input, you get your result, you backpropagate, and you update your data. So this is basically the same training scheme that you get if you were to train like a neural network. So this way it does okay. This gets like 97% accuracy on like an MNIST data set, which is about the same that you would expect if you were to train MNIST with like an SVM. So this technique is very similar to doing like classical machine learning on data. However, there's a second way that uses a trick out of quantum mechanics out of condensed matter physics called DMRG. And let me show you what that looks like. So the first thing we do when we train it in this fancier way is we pick 2 nodes that are right next to each other, or our nearest neighbor. And instead of contracting like, the bits into these nodes, we actually just contract these 2 nodes together. And then everything else around those nodes just get contracted as they normally would. So we pick two nodes, we contract everything else, and then we contract these two guys together. We save this larger tensor, like we put it off to the side, because what we're going to do is we're going to be calculating gradients of this guy relative to the loss. So keep this guy, keep track of this guy somewhere else, contract the rest of the tensor network, get your result, take the loss of the result. And so now what you're going to do is, instead of taking the loss relative to those two rank or those two order 3 tensors, you're going to be taking a derivative to this order 4 tensor. So notice that this tensor is going to be significantly larger than those two other tensors were combined. So let's say, like, maybe each of these dimensions were size 10. This is 10, 100,000, 10,000 parameters, versus if I had just those 2 order 3 nodes, they each would have 1,000 parameters. So I look for a total of 2,000 parameters. So the number of parameters in this guy is much larger, which means we're taking a gradient through a much larger state space. But yeah, take this guy, subtract the gradient, get a slight update. When we update this guy with our gradients, the next thing we do is we do the same thing that I described earlier, to where we take this node, we split it using singular value decompositions, and we throw away all except for the largest singular value. So we throw away all of the smallest singular values until this bond dimension was the same size as it was before. And then after we have these two guys updated, we plop them back into the tensor network, and then we move on to the next pair. So instead of being these two guys, maybe the next thing that we update is going to be these two guys. So then we update that, then we run with these two guys, and then we just keep sweeping back and forth until our model converges and is trained pretty well. So there was one researcher who ran this algorithm before, and he got pretty good results with MNIST. So it's an alternative training strategy that came out of the physics world, and it's still an open question as to whether this will always do better. There's some semblance that it seems to be doing better for certain types of problems, but it's still an open question as to whether this will work better for all problems. And so let's ask the question: why might this work better than just doing normal gradient descent? and why is the fact that we have like some results that this is working interesting? Well, one thing to notice is if I was to just do an SVD of this tensor after the gradient update and I didn't drop the lowest singular values, the bond dimension, or like the dimension of this edge between these two nodes, is going to be much larger than it was before. And so that's a really important thing to notice, is when we're taking a gradient through this big node rather than the smaller nodes, we're updating our parameters in a much larger space. And so that kind of looks like this. So I have my data. It's in a really low dimensional space, so things are pretty much nonlinear, or look very much nonlinear. When I combine those two nodes together and I'm taking a gradient through that, I'm actually taking a gradient through a much larger space. And so my data points are actually more likely to be linearizable, which makes them a lot easier to learn. But then when I go back down and I drop the lowest singular values, we lose some of the transformations, but the fact that we're keeping we're keeping the largest singular values means that we're keeping the parts of the transformation that are most important to our task. And so that allows us to get like some really interesting results out of tensor networks. And in fact, the fact that we can like do this type of thing and like take a gradient in a higher state space is something that's actually impossible right now with just standard neural networks. And so this is the reason why us at X are really excited about using tensor networks for machine learning applications, because it gives us a lot more power and a lot more freedom to explore, and it's a much more interesting like research topic. Cool. So yeah, like I said, this is something, so being able to take gradients in a higher state space is not something a normal neural network can do. And so that's what makes tensor networks for machine learnings very powerful and very interesting research subject. All right, so with that in mind, I'll be moving on to part 3.
Moving on to the next topic,
yes,
can we ask you a few questions?
Yeah, absolutely, go.
Okay, perfect. Someone asked if this truncation from one big MPS with bond dimension capital D to a smaller MPS with bond dimension less non-capital D, if that's truncation is trivially possible with the Tensor Network API.
Yes, it is trivially possible. And in fact, I forgot, let me show you how to do that type of thing in the Tensor Network API. So let me open up the Colab again. Eccentric connection, we'll skip all this. Already went over that. And that's how to do crazy stuff. Cool, node splitting. Yeah, so how do we actually like do this like node splitting in the Tensor Network API? Well, that's actually really easy to do. It's just tn.splitNode. And pretty much all you do is you say, what edges do I want connected to the U node or the left side? What edges do I want to connect to the right side? And it will split the node for you. And it will return these two nodes. Plus, if you decide to drop any singular values, you can see what singular values you dropped by this third thing that gets returned, which is the truncation error. So let's see what that looked like. So yeah, so after I split, I'm given these two nodes. They're very clearly non-unitaries. But what I can do is if I merge these two guys together, you'll see that the result is equal to the result that, or like the matrix that we originally started with. I can also drop singular values. So in this case, I'll say I only want to keep the top two singular values and I want to drop the lowest one. So if I was to do that, so I split this thing, you know, edges on the left side, edges on the right side. After I combine U prime and V prime together again, we can see that the lowest singular value, which would be represented by this 1.5 on this diagonal matrix, got dropped. So it got zeroed out in this case. And we can see that the third argument of split node returned truncation error. So we print off truncation error. We see that the lowest singular value that got dropped. I can also keep only one singular value. In this case, it would only keep 2.5. And we'll see that 2 and 1.5 both got dropped. So yeah, split node is the method that you're looking for in Tensor Network. And what's really cool about what I really am proud of with the split node function is you can set up and you can split this thing. So in this case, you know, I just have an order 2 tensor, so it's not too interesting. But you know, this thing works for an arbitrary order tensor. So if you tried to like do this splitting with SVDs by hand, it's very likely that your reshaping and transposing to get it into a matrix form is going to be bugged. Versus here, it's really simple. It's like if I wanted to split this node with like an order 5 tensor, I would just pick what legs I want on my U side, what legs I want on my right side, and I'm good to go. So yeah, one of the things I really like about the TN library. Was there another question?
Yes, we have another question. Does the Tensor Network support SciPy sparse array internals?
At this moment, no, I do not believe so. But that would be something that we could add pretty easily if it gets requested. Actually, I'm just going to read the Q&A. Cool. So the next question is, this is what we call a 2-site update, but is there also a single-site update? And also, you can create your own 3 or 4-site update way. Don't quite understand what that question is asking. So I'll just skip ahead. Is this a guess, like we guess QML being advantageous with classical data, or is there a formal proof that this DMRG is more advantageous? So it's more than just a guess. DMRG has been used in physics to find ground states all the time. And finding ground states is very similar to finding like a good set of parameters for your model. So it's not quite the same. And then also the thing is with QML, our team actually doesn't quite believe that QML is going to be useful for classical data. And there's really, so QML is quite out of topic of this conversation, but I'll say it anyway. There's actually very little evidence that quantum computing can help with like classical data machine learning algorithms. However, QML is really useful for quantum type data. So things like, let's say you had some measurement device that could pick up like the quantum state of some molecules and you could import that into your quantum computer. QML would be really, really advantageous in situations like that. And so that's when we talk about QML, that's what we focus on. in our research on our team. Let's see, next question. Oh, getting lots of questions, sorry. Also, when training an image based on data sets like MNIST rather than constructing a large MPS, is it possible / efficient to directly approximate the 40 tensor represented by the convolution? Do tensor networks inhibit strong model compressibility properties? Yes. So for convolution kernels, we haven't tested that yet. That's actually still one of the areas that we're researching actively right now. But for dense layers, your type of intuition is pretty much correct. And I'll be going over an example of that very soon. And then the last question is, yeah, but that's quantum data. That's not a question. Cool. I think that summed up most of the questions. All right. So let me switch back one more time to my slides. There we go. Cool. So yeah, part 3, tensor network, neural network hybrid. So the goal for this presentation, or the goal for this using tensor networks inside of neural networks, is to make the inference time faster for our machine learning models that we care about. And so here's a question that a lot of people surprisingly don't know. So what is the slowest part of a neural network for inference? And this is pretty much true for every single neural network that exists in production. And the answer is the fully connected layers. So any like large, dense matrix multiplication inside of your neural network is going to be by far the thing that takes up the most compute. And so I'll give you an example. I think we have a hardware team at Google that's working very, very hard at building these TPUs, which are basically these hardware things that are used to accelerate neural networks. And literally the only thing the TPU does faster than like a GPU is makes matrix multiplication wicked fast. So if we're actually able to decrease how many flops we need for that mapmul in our model, that would help us a lot, as well as other companies who use machine learning models in production. So let's talk about how we actually do that. So we've done that before. We've done that successfully for our research. And this is basically what it looks like. So if you've ever seen like an ML model, if you've ever taken like a machine learning class, you've almost certainly seen an equation that looks like this. So basically all this is X is your input vector to your layer. This can be like your actual input data, or this could just be like the output of a previous like layer in your neural network. We take this vector, we multiply it by some weight matrix, we add a bias term, and then we pass it through some nonlinearity, be it tanh, ReLU, swish, doesn't matter. It's just some nonlinearity. And so the part that we focus on our research and for using tensor networks is to take this vector weight multiplication part of the neural network and replace that with the tensor network, leaving pretty much everything else untouched or like relatively the same. So let's talk about how we actually do this. So the first thing you might notice is X goes from being a vector to an order 3 input. And you might be saying, Chase, how the heck do I go from a vector to an order 3 input? This was actually the simplest thing to describe. This is just basically a simple reshape. So I have this 512 vector, or like this 512 list, and I just turn it into an 8 by 8 by 8 cube of numbers. And it's no more complicated than that. It's just a simple reshape. And then quick refresher on node splitting. So remember, what I can do is I can decide what legs I have on the one side, what legs I have on another side, take an SVD, drop the lowest singular values, and then I'm left with 2 nodes that is a compressed version of what my original node was doing. And so this is basically what we're going to be doing with our weight matrix. And so the first thing we do is we take our weight matrix, we reshape it. So we take this 512 leg and we turn it into 3 8 by 8 by 8 legs. And we do the same thing for this one. So we turn this 1 leg into 3 legs. We do a node split. So we split right here, putting these 2 legs on this side and these 4 legs on this other side. And we only keep some of the singular values. So usually what would happen is the number of singular values you'll see will be the min of the product of these 2 sides. So in this case, it would be 64, since that's 8 times 8. But in this case, we're only going to keep the top 8 singular values. We do the same thing on this node. So we split here, putting these 3 legs on this side, these 2 legs on this side. And then we're left with a matrix product state that looks, or matrix product operator that looks like this. So the first thing you'll notice is that this tensor network is a lot smaller than the original weight matrix. So the total number of parameters in the original weight matrix was around 260,000 versus in the new MPO, it's only around 5,000 parameters. So a huge drop in the total number of parameters. And then likewise, if you were to actually do like the flop calculation to contract this tensor network versus this tensor network, the number of flops you need to contract this is substantially smaller than to contract this. And we won't be going over that just because it's just like a lot of like math. But just believe me, but that's true. Cool. So there's 2 ways of training a model that uses a tensor network. The first way is to actually like literally do these steps to where you split the node. So maybe you'll like train your weight matrix, you'll split the node, you'll be given your low rank approximation, and then maybe you do some fine tuning to correct for any errors that might accumulate, especially if you do this on like multiple layers. So that's one way. The second way of doing it is to just say, you know what? I'm just going to pretend that I did all of this, but not actually do it, and just train my neural network with this setup from scratch. So I would start with my MPO, randomly initialize these nodes, and then just backpropagate and train these guys like I normally would. It turns out those 2 methods work pretty much similarly. So we've tested this on a couple models, and both methods get about the same final accuracy. So generally what we recommend for people who actually want to try this IRL is to just start with the MPO setup and then just train with that from scratch.
Hi, Chase. We have a question. How does one decide which eigenvalues to drop? Is there any formal proof of that decision?
Can everybody still see me? Or can still hear me?
Oh, we can hear you, but can't see your slides.
Okay, cool. Yeah, sorry, Zoom crashed on me. Don't know why. Weird.
Oh, sorry. So I was saying we have a question. Did you hear the question?
Yes. Yeah, I'll read the question. Okay, cool. So the question is, how does one decide which eigenvalues to drop? Is there any formal proof of that decision? Yeah, instead of eigenvalues, we consider them singular, or we only care about singular values. And yeah, so the singular values that we drop are the smallest singular values. And the reason why we only drop the smallest singular values, and there's a really good mathematical reason for this. Let's say we took a matrix, and I decompose that matrix and drop the lowest singular values. That is provably the best way to compress a matrix while maintaining the smallest error in your L2 norm of that matrix. So that basically means, like, if I had my original matrix, I multiply it by a vector, and then I take my decomposed version, multiply it by the same vector, the L2 difference between those 2 vectors is going to be as small as possible. And so that's why we drop the lowest singular values of our tensors. Yep, good question. Cool, yeah. But for the most part, we don't actually do these steps. And in fact, like with the things we do at Google, we never like literally take the SVD. But this is like a good mathematical reason as to why this should work. And as you can see, the results are really good. So again, this is the same transformer of the demo that I showed earlier in my presentation, to where I had the original version had over 236 million parameters, versus the tensorized version only had about 100 million parameters. And then the inference time to generate every single word in the sentence, it was about 0.2 seconds to generate a word with the original transformer, versus 0.81 seconds for the tensorized version. So a little over twice as fast. And also, as you can see, the log perplexity, which is like a relatively good score to measure how well your model generates sentences, are pretty much identical. So 3.2 versus like 3.3. So like you take a very tiny hit to your model, but you get a really big improvements on your inference time for that model. And actually, in some cases, we've actually seen, because the tensor network works as a regularizer, we've actually seen some models actually improve their performance because they're no longer overfitting by doing this low rank decomposition. And this is just the demo again that I had at the start, just to get the feel for why we actually want to do these types of, you actually use these networks within our neural networks for like production type use cases. Okay, and I'll leave it up for if anybody has any questions. Yes. Does the TN library parallelize the computation in the backend? How can use CUDA along tensor network? So yes, so that's a good question. So it depends on what you mean by parallelization. Actually, this is let me go back. Let me just show you something. So yeah, so you can use tensor network on GPUs, and let me show you how to do that. Let me just switch back. Yeah. So woohoo! Let me show you what it's like to run these things on GPUs. So first, what I'm going to do is I'm just going to give my Colab a GPU. Prove I'm not a robot. Let me get back up. All right, we should be good. Cool. So how I'm actually going to use a GPU to accelerate my computation with tensor networks is there's multiple ways of doing it. You can use these deep learning backends. We support 3 right now. They include PyTorch, TensorFlow, and JAX. JAX is our personal favorite on the team, and let me just show you how to do that. So if I scroll down here, I'll show you how to speed up your computation with JAX. So this is, so if you remember back in my slides where I had that triangle of tensors that represented the trace of A times B times C, that's all this tensor network does. So that's literally the calculation I'm doing. The first version I'm going to do is I'm just going to run it on normal NumPy. So basically I'm going to use the CPU. And then the second version I'm going to run is I'm going to use JAX, which is going to run on the GPU. If you've never used JAX, I highly recommend learning JAX. It's outside of this talks, but JAX is awesome. It's super cool. It's like the best thing ever. So yeah, you should all learn JAX. Anyway, so yeah, so we're just going to do some time its to see what how much speed up we get by using the GPU versus just staying with the using CPUs. So this takes a little bit of time to calculate. Beautiful. So as we see, the NumPy backend took 3.6 seconds to do the calculation on the forward pass, versus JAX was able to finish the exact same calculation in 93 milliseconds. So that's like what, a 30x speed up over the original version? Yeah, pretty fast. So yeah, so that's how you would use GPUs with tensor network. Okay, I think that one's good. Is there an automatic method for decomposing current neural network representations into equivalent tensor network architecture? So as of right now, no. We are working on building Keras layers that have these tensor networks pre-built inside of them. But as of right now, we don't have a way to, like, if you give me like a dense layer, to decompose it. That doesn't mean you can't do it. Like, the tensor network library fully supports doing those types of things. It's just we don't have it like pre-built right now. That one's good. You mentioned that you don't really perform the SVD operation. How do you compute the singular values without performing SVD? Right, so good question. So I think you might have misunderstood a little bit. So if I go back to let me go back to the slides. So I think you are meaning this, yeah. So the question was, if I'm not actually performing SVD, how do I calculate the singular values? Well, the answer is we're not calculating the singular values either. Basically what this is how you would mathematically think about why you would want to use a tensor network within your like neural network architecture. But that doesn't mean like you actually have to decompose anything to use it within your neural network architecture. Basically what you do is, instead of like having your dense layer or like your weight matrix in your neural network be represented by this guy, basically your dense layer is just going to be represented by these 3 tensors instead. So we don't actually, when we're training a neural network model, we don't do any SVDs because we're starting with this guy. We're just assuming that a tensor network is going to work, and we're training it that way. I hope that answered your question. I am confused with the second section. Is the claim that DMRG performs better when training classical data? If so, is this provable one? So the word prove and machine learning don't really go too well together at all anyway. So I don't really have a good answer for that, mainly because like proving anything in machine learning is really, really hard. So no, there's no proof, but there is empirical evidence that we see it do better. Okay. Are there any other questions? Yes. How are we selecting the number of parameters for decompose if we aren't doing SVD? It's just a hyperparameter. So you would just decide what that bond dimension between the two nodes is before you train the model. And if it doesn't do, and so you would have to do like it's kind of like picking a learning rate. It's like, well, how do we know what learning rate will go well with our model? Well, you don't know. And so you just have to try several ones or do like hyperparameter tuning to see which ones do the best. Okay.
I believe there's one more question about finite MPS. There's a three-part.
I'm sorry, I don't. Could you read the question out loud?
Yeah, I can read it. So first, this is an implementation question since I've been using TN for a while now. Thank you. The first question is, in the finite MPS module, the input gate indexes are defined as 2 and 3. Is there a reason for this? I was using 0 and 2 and now I need to reorder for my code to work.
So I didn't build the MPS module, so that sounds like that would be a great question to ask on the GitHub issues, because that sounds like a bug. So I would ask there. So I don't know the details of the finite MPS module because that was built by one of our collaborators at Perimeter Institute. So yeah, if you have a question, like a technical question like that, like feel free to like raise a GitHub issue, and please do so.
Great. The second question was, for general finite MPS, is the only way to truncate going through each pair at a time?
It's the only way to truncate going through each pair at a time. Yeah, pretty much. There isn't really a lot you can do to make that faster.
Also, and the third question from this person was, how can one make a copy of a finite MPS efficiently?
There should be a copy operation on the finite MPS, is there not? Again, so the finite MPS object in the tensor network is relatively new. So if you have issues like this or questions, like please raise a GitHub issue, because that's the best way we know how to or like what to fix or like what features to add to the library. But the finite MPS should have a TN or should have a copy operation. If it doesn't, we should add it.
Great, thank you. There's another question from Ryan. I think you might be able to see this one. If you want to, or I can read it to you as well.
Yeah, what was the question?
Yeah, so the question is, how do you deal with issues on scalability? It seems that MPS for MNIST wouldn't scale as well if, for example, the pixels were higher dimensional or the image was larger than, say, 512 by 512.
That is a outstanding question, and that is still an unsolved problem. So yes, so for the tensor networks, like, so for the most part, like MNIST is just used as like a test data set to see if our ideas work. But you're absolutely right. So scalability is one of the things that we're still like struggling with. And in fact, in the MNIST paper that came out of what was that group? Oh, I don't remember what. So Miles Strodeneyer, who's the main author of that paper, he actually didn't even use the 28 by 28 pixels. He downsampled to 14 by 14 to make it a lot easier to train. So yeah, so that's a great question, and it's still something that we're struggling with.
Great. I think that's all the questions for now. If you guys have any more questions, please feel free to ask them in the Q&A.
Okay, great. Thanks, everybody.
Awesome. Yeah. Thank you. I think the Stanford leadership team will be on for a little longer. If you want to, and maybe Joe and Chase, you can stay on for a few more minutes. But yeah, thank you so much. Jessica, you want to? Oh yeah.
Oh yeah. Thank you everyone for coming. We hope you enjoyed it. You can see more information on our website, stanfordquantum.com, and we'll try and send the videos and other things. Yeah, I think that's pretty much it. Thank you, Chase, for a wonderful presentation.
Yep, thanks everybody.
Great, bye.